Hello, welcome back to practice problems of week 10, fall 2021 of Intro to Electrical Computer Engineering. I am Dr. Roberts, or I am a YouTube video of Dr. Roberts, or maybe an impressive AI, who knows, you can't see me. In this problem, right, so for the first four problems, we're doing passive circuits, and you went through and we derived a couple of different filters and saw we use voltage dividers quite a lot. Now, practice problem 5 goes off the rails in that we're throwing our active component in here, our ideal op amp, right? And so, but, you know, don't be afraid. And the problem asks first, what type of filter is this? Or what kind of filter, what kind of, maybe it's not a filter, it's an amplifier. Better word here. Can't remember my typo or not. And then also calculate the gain of this circuit if we have R1 is equal to 5 kilo ohms and R2 is equal to 35 kilo ohms. Now, when you see an active op amp, really we just have to remember some certain rules about ideal op amps, right? So we know for an ideal op amp, by definition, that the voltage at the positive non-inverting input, V sub P, has to be equal to the voltage at the inverting negative input. So V sub P is equal to V sub N. By definition, this has to be true. So we can use that to our advantage, right? We also know that the current going into this one, I sub N, and the current going in here, I sub P, we also know that I sub N is equal to 0 by definition, and I sub P is equal to 0 by definition. So we could take advantage of that. Now, how is this useful? So if I look at this circuit, right, I have V in here and it connects here. So this is VP right here, right? So I can draw it. So this is VP and this is VN, right? They're connected to the wire. So I say that I know then that VN is equal to VP, right? They're the same wire, so it's the same voltage. And by definition, I know that VP is equal to VN. So this is Vn, right? So Vn is actually equal to Vn. And this wire goes all the way down to this node, Va, which is equal to Va. Right? They all have to be equal on the same wire. Therefore, Va is equal to Vn. Well, that's convenient. It sets this up. Now, so I have this voltage here. We can add some currents, right? So let's add, we'll call this I2, and we'll call this I1. Well, now we should have enough information to solve if we just look at this node here and we can do KCL, right? So if we just do KCL at this node, right? So we can do KCL at A. And so if it's in, it's positive, it's out. So I1's going out, so we get that is equal to minus I1. This is going in, plus I2 minus IN is equal to 0. We know that this is 0 by definition, so we can get rid of it. So we get these, and now I can move it across, and I see that I1 is equal to I2. So we have this relationship. That makes sense, right? If nothing's going there, whatever flows in here, so the current's the same. Now, let's write some equations for this current using Ohm's law. And if you recall, right, if we draw our Ohm's law equation, right, is in class, you say, okay, if we have some resistor R, some current flowing I, right, we can define some voltage across it, V, right? So there's some voltage drop across resistor. And you could think this is delta V, right? It's some change, right? So Ohm's law, we know, says V equals IR, or have you know, that's some change in voltage, delta V, right? What does that mean? So if what is this voltage? So if I have a measurement and the voltage up here as the V top and the voltage on the bottom here, bottom, right? So if we measured it, well, we know that this V, this delta V, this change in voltage is going to be equal to V top minus V bottom. So at any point, one way we can express Ohm's law is we can express it as a fraction. Now, if we want to solve for the current with Ohm's law, we can say, oh, okay, well then I is going to be equal to delta V over R, just rearranging. So, or I is going to be equal to V top minus V bottom over whatever resistance. Right? And this form becomes very convenient when we work with op amps. So, if we want to reuse Ohm's law here for I1, what do we see? For I1 then, the top is VA, so it's going to be equal to VA minus ground is 0 divided by R1, right? And we know that VA is equal to VN, right? We saw that previously, so we can say, okay, that's equal to then Vn over R1. So we have a relationship for I1. We can similarly write a similar equation for I2, where here V top is going to be equal to V out minus the bottom is equal to VA over R2. And again, we know that VA is equal to Vn, so that's equal to V out minus Vn over R2. Okay, now we have these currents defined as voltages, and we want to know the relationship in voltages, and we have these equations. So let's substitute in these equations here. So this one is for I1, so I can write that as then Vn over R1, and then is equal to I2, which is this, is equal to V out minus Vn over R2. And we're doing all right. So we're like, okay, so what do we do here? Now let's just distribute this out. So it's a little bit easier to see. So you get that Vn over R1 is equal to V out over R2 minus Vn over R2. And now I can rearrange to put everything on one side, right? And so if I do that, what I can see is that I get Vn over R1 plus Vn over R2 is equal to V out over R2. Let me get another piece of paper here because it's running out. Keep the good times rolling here on this derivation, right? And I'm kind of like in this weird one column here. So we have this value here, and hopefully you're happy, right? Now, if we keep going, we can then say, okay, well, let me just pull out this. So we say that it's equal to Vn times 1 over R1 plus 1 over R2 is equal to V out over R2. We can now multiply across by R2, and we can actually divide by V at the same time. And if we do that, we get R2 times 1 over R1 plus 1 over R2 is equal to V out over Vn. And now we can distribute this through, and we can just flip these sides. We get that V out over Vn is going to be equal to R2 over R1, R2 over 1 over R2 plus 1. So there's our gain. And what we see then is that the gain here is positive. And so this is what type of filter is this? This is a non-inverting amplifier. Right? And one way to look at that is the input's connecting to the non-inverting positive input, so that's kind of a giveaway of what it is. Now, if you knew this by inspection, and you knew the gain equation, well, then you could substitute right in. So now we can then calculate the gain for that. So if R1 is equal to 5,000 ohms, and R2 is equal to 35,000 ohms, right? We get that the gain V out over Vn is going to be equal to 35,000 ohms over 5,000 ohms plus 1. Right, these all cancel, so that's equal to 7 plus 1. which is equal to 8. So this will have a gain of 8 in that case. Pretty interesting. And again, if you can identify this and know the equation, you can save yourself some trouble, but this is how you drive it out and how you do it. You can see again with a op-amp circuit, all we're doing is we're applying these op-amp rules, right? Knowing that these voltages have to be equal, knowing these currents are 0. We use that to set up a very simple KCL relationship. Then we don't even use this, right? We ignore it totally. And if so, we can solve for the equation. And with that, I will see you in practice problem number 6.